Hello everybody, hope all of you are doing well. Today we are going to talk about introduction to robotics in this lecture, and we are going to see overall concept of the robotics to understand a comprehensive and general view of what are the robots and what are the different applications and what are the different solution methods in very general view, plus the architecture of the robot hardware. So, as some resources that you can have a look and understand the robotics, we have different, actually too many resources for robotics, but some of the most popular ones are including probabilistic robotics, robot modeling and control, and introduction to autonomous mobile robots. That these three books are pretty nice to having the understanding of robotics, and they have, depending on what you want to do with robots, each one of them can be useful for the application and a specific robot type that you are going to learn and work on. So if you want to have a general understanding of key elements of the robot development, we should say that, okay, first of all, as we may know, the programming topics is one of the important concepts that we should know. So the basics are important to understand. For example, if you have a robot, that robot wants to go and open the door and go outside, for example, then you should be able to write your code in any programming language that you can bring it into the robot and specifically specify each one of the steps in simplest form. For example, robot, if it's wheeled, turn left, turn right, and go toward the door and detect the stop in proper position, grasp the door handle and try to open it. And all these steps precisely should be defined for robot. That comes from programming skills. Then we have mechanical engineering. That if you are developing your own robot, or even though you have the platform or existing robot, you need to know the most basics of mechanics, that how the robot is linked together, what is the joint of the robot, and how the joints of the robots are connected together. And to do this, one of the starting point is to understanding the modeling and 3D modeling and design applications and softwares. That makes everything easier to design your own robot, model it first, see everything is working, then you can bring it to real life. This can start from like SolidWorks or any CAD or 3D modeling design in order to develop your own robot. But also you can for fabrication, you can use recent technologies of the 3D printer that all are coming from 3D model design. On the other hand, as third important element, we have the electronics. You need to know basic concepts of the electronics, how to power in simplest form as a starting point, how you should power your robot on, and of course, having microcontroller, how to write your code inside your microcontroller, and how inputs, outputs are working there, how you can send instructions to robot, how you can read the sensor, and what are the input outputs among those. Even we say, okay, let's say we don't want to design circuit and we don't want to design our controller. Let's say we have it already. Indeed, although you have it, but still you need to know, okay, how is like, you should know that if you have a cable that has USB, you should plug it to USB port. This is the most element basic thing that you need to know, and it goes toward like understanding the UART communication, I2C if you have sensor that works with I2C, and different knowledge over there. Besides, in order to propose proper solutions for your robot system, you need to have simple math skills that you can understand probabilistic concepts of robots. That today we will going to a little bit talk about it, and how you can do simple calculations of the, for example, finding distance. of the robot and the obstacle or the wall. On the other hand, you should know the knowledge of the different kinds of robots, for example, mobile robots or fixed kind of robots that in according to control and work with robots, you should know what kind of sensors there are and how the sensors are working. General familiarity with the different kinds of actuators, how a robot can act, what kind of different actuators we have, and even we can push it forward further and say that we want to understand how to control them with different mathematical techniques or control techniques like forward kinematics, inverse kinematics, how your robot joints are connected to each other, and how we can control robot and effector in order to move in the environment, for example. So you may have a look at this and say, oh, this is so complex and too many things that we need to know. Actually, if you are in the starting point, you don't need to be like expert in these fields. You start from the most basics of each one of these, and one by one, you learn them during time and working. It depends on the requirements, and if you are designing robot or if you are working with your robot one by one, you start to learn them. That of course it's quite possible after spending some time you become more expert. In today's lecture, we are going to talk about, first of all, answer the question, what is the robot? Then distinguish robots into two general types of the fixed robot and autonomous mobile robots and see their characteristics. Later on, we will move on talking about the common types of sensors for robots, what are the available options, and what are their applications, and what we should do, what we can do with them. Later, we will see the general structure of the robot design. So we will see different layers of the robot control design and how they can work. Afterward, today we are going to see some application examples for different kinds of robots, and we will see also example challenges for robotics. There are many different examples that they are challenges that developers, researchers are working to solve them. But one of them, for example, we will see as example is localization, that we will talk about it. Later, we will see also one example solution. There are different techniques, algorithms to control your robot. One of the recent most popular one that becomes more trend is using learning algorithms, namely reinforcement learning. I will just have a brief introduction of what is it. Then after finishing today's course, you are going to understand the general concept of robotics and having a general overview of what is happening in robotics and how you should consider to develop your knowledge to understand more in depth of the robotics. So the objective is to having the simplest understanding of robotics for today's course only. So, first of all, we should answer the question, what is the robot? The simplest definition for this question is that we can say we have a device that can interact in the environment. Then we can call it robot, that senses the environment, makes some decision perhaps, and acts in the environment. And that's, of course, distinguishes with some machines that the machines like laundry machine is different with robots because usually they are not in place that sensing the environment and acting in the environment. On the other hand, if you want to answer, okay, if you have a robot, this robot usually is supposed to do something in the environment, and one of the way of understanding of the surrounding environment is constructing a map of the environment in surrounding environment. Understanding if I'm a kind of robot that's working on table, where is the objects? if I'm robot that moving in the street, I'm constructing the map of the environment in order to understand what is happening around me in order to make proper decisions. This is what like human being does. So if you want to have a look at a brief history of robotics, we can say in 1500 Leonardo da Vinci designed such a robot, and you can see some sketch that he was designing, and of course you may know this robot in some movies. In 17th century, automated machines were built that were able to move and interact in the environment in simplest form. And we have one sample in Germany in the museum that if you have a chance to go, you can have a look. On the other hand, in 19th centuries, we had robots that they intended to play music. These are kind of a starting point of where the history of robots started. On the other hand, we have Isaac Asimov, that was a writer and writer of science fiction stories, and he was a doctor of biochemistry. That his robotics, he introduced rules of the global understanding of the how should robot be limited in some rules that this made him quite popular, and those rules were like stated: the robot should not cause harm to human being, the robot must comply with human issued orders unless it violates rule 1. And as third rule, he said that the robot must protect its existing except in case that result in violation of first and second laws. And based on this, you maybe have seen, I'm sure most of you have seen the iRobot movie in 2004 that tried to play the rule under around these three rules. Of course, this is like kind of a very basic general understanding of what may we face in future, but for now, and of course we should have specific rules, especially for machine learning developments. But anyway, today we are going to only talk about general understanding of different kinds of robots. So, if we want to talk about general category of robots, we can split them into two general categories. One is fixed robot, that you may have seen industrial robot arms. In industry, they are doing they are engaging in different kinds of applications, including pick and place, including, for example, soldering, welding, or many different usages like painting, and quite popular. On the other hand, we have mobile robots. That mobile robots basically are capable to move in the environment, and we have quite different types of mobile robots. If we want to talk about main features of them, for example, if we want to talk what is the mobile robot in more detail, we can say they have, of course, displacement capability in the environment in simplest form. They have ability to understand the environment, but different kinds of sensors that they have. We are going to talk about what kind of sensors that we can have. And there are pretty popular robots nowadays. We have Spot Robot from Boston Dynamics, one of the popular companies that is developing pretty capable robots. And we have Stretch, that we have AMR or AGV, the robots that can move on the wheels, plus industrial arm mounted on that makes it mobile robot. What are the different kinds of mobile robots? We say they are robots that can move. They use actuators to act in the environment, and that their different kind can include flying robots, walking robots, swimming robots, running robots, etc. Any robot that is moving in the environment, and they are using different kinds of perception systems to observe the environment and understand surrounding environment. This can be include camera, LiDAR scanner, infrared sensors, and etc. So camera you are familiar with, but LiDAR scanner is kind of a scanner that gets the distances of the objects from environment and can make 3D 3D mesh, 3D point cloud or 3D mesh of environment that shows you the distance usually, and it's a laser sensor that rotates with a mirror in order to get the distances from surrounding environment. An infrared sensor is quite similar task to find the distances in the environment. Usually robots in the environment try to interact, try to move around to get knowledge of the environment. And when we are talking about environments, usually in robotics we categorize them into two. As indoor environment, that robot is working inside the building, and that there is usually not open area. On the other hand, we have outdoor robots, or robots that can work on outdoor environment, and as their name is stating, they are working in somewhere that is outdoor. And for both of these, we have environment model usually, as we stated, as mapping or constructing the kind of any simplest understanding from environment, even distance of the where the robot is with the obstacle or wall can be understanding or modeling of the environment in order to autonomously be able to detect the to have proper decisions in the environment. On the other hand, in contrast to mobile robots, we have fixed robots that they have pretty similar features to mobile robots, but only the difference is that we can say they are fixed, they don't move in the environment. The most popular ones are industrial robot arms that they usually are installed in somewhere fixed, and they need to do some manipulation task or some simple or complex defined pre-ordered design tasks for you to run. So if I want to mention some important research tasks about these robots, today we are going to talk generally about robots, but if you want to know about the research topics, we can say visual servoing is important there. It means that like if you have a camera on your robot arm in industrial arm robot, how visually by seeing the object can control the robot in order to grasp it, for example. We have object placement, that how robot can take the object, grasp the object, and place it somewhere else. That trajectory planning, how robot hands should move, if there are obstacles, what to do, what's the speed, and if there are the different weights of the object, how to do, if there are external disturbances or external push on the robot, what to do, and all of these are together can be called as manipulation even. And there are a couple of more. These three were most important ones. So, as you know, we said that we have robot can do something in the environment, act in the environment, and also sense the environment. So if you want to talk about common types of sensors in robotics, we can say vision, to get visual perception of the surrounding environment. So this can be simple camera, webcam, or this can be real sense, or a sensor that has stereo camera, or a sensor that has complex IMU combination, stereo combination inside, and RGBD, the sense the cameras that not only can detect the colors RGB, but also can color the depths of the environment that color RGBD, and there are different kinds of combinations of these vision cameras or vision sensors. A second category, we can talk about the tactile sensors that robots can sense the environment by touching, by any proximity to any obstacle, or anything like your finger that touches the object. As third element, we have the fourth categories of sensors that your robot can detect amount of force on the for example joints. If you push your robot arm, how much force is in robot elbow or shoulder or any joint that we are talking about. As another classification for sensor type, we can say we have distance sensor. That distance sensor again has too many different variations. That basically the simplest thing that they want to do are measuring distance. As I explained to you, distance sensor can be LiDAR scanner, or can be a simple infrared sensor, or a solar sensor that measures the distance by the sound waves and the time that it goes and comes back. On the other hand, we have sound sensor or acoustic sensors that they are kind of microphones, and robot can hear the surrounding environment like as human does. So if you want to talk a little bit more about the acoustic sensor as one of the sensors that is still under development, is estimation of the sound source location, can be in 3D form, and the robot can try to detect the definition and the source of the sound where it is coming from. So in order to do that, robots should equip with microphone array to understand the surrounding, and there are different tries to do this, so that you can see one of the models that here there are different resources to different sources that separated in 360 degrees in order to understand where is the robot and based on the current position of the robot, where is the relative position of the other sound source. This is very interesting application to be combined or fused with other kinds of sensors in robotics. Not only seeing what is happening, over 95% of robots are only relying on vision and different kinds of vision sensors, but also this can be very interesting research that how robot can understand the sound. If we want to talk about general architecture of a robot system, we should say robot system has mechanical structure. Mechanical structure includes actuators. Actuators can be in different types. One of the most popular one is electrical actuator, like servo motors. If you have heard ever about, for example, robotics, servo motors is one of the most popular example in robotics. That you have servo motor, it means that you have a DC motor inside, and this DC motor connected to gearbox, and this gearbox is a pack of the controller board, that this controller board controls everything inside in order to, for example, simply have position-based control. What do I mean? It means that if you have a robot joint arm, and if you have a motor in one of the joint, then you can change the position exactly with your programming language. You can say, okay, from 0 degree, go to 90 degrees. Then that board inside controls the DC motor and the gearbox, how much to rotate in order to go to a specific position. So this is like servo motor. We have different types of electrical motors. Of course, I cannot explain in today's course. If you are interested in have a look, any motor that works with electronics. On the other hand, we have the hydraulic actuators. That in hydraulic actuators we have a tremendous amount of torque because they are basically working with oil pressure, and that those are like kind of used in industrial and big robotic systems. On the other hand, we have pneumatic actuators. That pneumatic actuators is working with air pressure, similar to hydraulic, but pneumatic ones. Pneumatics ones are they have less torque, but less challenge in some perspective too. Besides, in robotics, we have artificial muscles that is still they are heavily under development, and artificial muscles they are trying to this kind of actuators is trying to mimic human joints, like human muscle. We don't have any actuator directly; we have muscle. So in robotics, also many research studies are working on developing this kind of sensors. One small point here before I forget, the one of the advanced robots, that humanoid robots that we are going to see, also they have from Boston Dynamics, they are able to control the robot with hydraulic or oil pressure. So mechanical structure, we have kinematic model of robot. Kinematic model of robot means that we have how your robot joints are connected to each other. If you have robot that looks like human, or a robot looks like wheeled robot, how the motors connected to wheels and how configuration is, we call it as kinematic model. On the other hand, we have dynamic model. All the variability or the movements of the robot, if we are going to study them, we can call it as dynamics of the robot, or dynamic model of the robot. And of course, if you go in depth, you will see what are the applications. For example, in robot control, motion control model, that we have it for advanced techniques. We usually try to formulate the kinematics model and dynamics model. That, for example, I formulate these in my Islam class, simultaneously localization and mapping for robotics. On the other hand, beside the mechanical structure, we have the controllers and computational power that you have board, you have IC on the board that controls your robot, or you have a computer, mini computer, for example, Intel NUC, or Raspberry Pi, or Jetson, different Jetson Nano, for example, that you can program, have operating system inside sometimes, and write your code that it runs for you and controls everything. On the other hand, in architecture of robotic system, we have sensors, we have electronics and power conversion units that makes sure that your actuators are working, sensors are working, your controller is working. And if you want to have a general look at the robot structure, very general look can be looking like this, that we have a controller that mounted and controls a mechanical structure, including the actuators and links and everything. These mechanical actuator mounted some sensors on that sensors can detect the environment and give information to controller, and this controller again control the mechanics. All these components usually are connected with electronics together, some circuit boards. So, if you want to have a general perspective of the robot architecture, let's say you have a robot. This is AMR with industrial robot arm on top of that. In the lowest level, we have the sensor interface and actuators interface that you can control them. So what we say, These are driver layer that you have some simple programs to read the sensor and control the motor, depending on what sensor you have and depending on what actuator you have. On the other hand, one layer higher, we have platform layer in robot architecture that can include, for example, kinematics, again, how robot links are connected to each other. We can have image processing, the robot vision that sees the environment and processes the information. For example, if you have camera, webcam, you are seeing me now, for example, and the same thing robot can see, and we can have algorithms on top of that to detect, for example, a specific color in simplest form, or an object. We have sensor fusion topics in platform layer, meaning that if you have a couple of different sensors, you have a sensor that measures distance and the sensor sees how to merge these together. We call it sensor fusion in robotics. We have steering that says, okay, in platform layer, how we can control robot. If you have like wheeled robot, like car, how you do the steering, turn left, turn right, or these kind of control things. About this driver layer and platform layer, we have algorithmic layer. In algorithm layer, you can have different kinds of algorithms in order to control your robot. One of the popular ones is trajectory planning, for example, or path planning. So for path planning, you say my robot from point A, from room A wants to go room B, then how my robot can follow the path. So you can write algorithms to generate this path. This can come from artificial intelligence algorithms, machine learning, or simply some if-elses. If the distance is smaller than this, do this, do that, do that, do this. On the other hand, it can be trajectory planning. Trajectory planning is also more popular for industrial robot arm. For example, if your robot's arm is moving, you are generating the trajectory of movement. How this should be generated, again, there are tremendous number of algorithms in order to do that. Optimization algorithms or simple sequences of motion captures. In algorithmic layer, we can have obstacle avoidance. So if there is obstacle, how to pass it. Or we can have more complex algorithm like SLAM that is stand for simultaneously localization and mapping, and it means that if your robot moving in the environment, how at the same time localize and how at the same time map the environment. About localization, we are going to talk briefly today, but mapping is like kind of constructing of the understanding of the surrounding environment. Then also we have user interface layer that is can be used for developer as me, like robot diagnosis, teleoperation. I want to with joystick control my robot, monitoring to see what robot sees, and video and image display can be a layer. So this is very general and important layers of most of the robots, from simpler robot to complex robot. Some of the robots have more components, some of the robots have less components. But when you are looking at the robot, you should have like understanding like in this few layers. All right. Now, as one of the interesting robots, we said that we have two general types. One of the types is mobile robot. So what are the challenges for mobile robots? Because fixed robots are pretty similar to mobile robots, they are only fixed. Because the industrial robot arm with AMR can move, for example, in the environment. So what are the challenges for mobile robots? We can say, first of all, they need to answer where am I? Basically, that we call it as robot localization. So if your robot is somewhere in the environment, should know where it is, right? In order to do something. On the other hand, the second question that a robot should answer as mobile robot should say, where am I going? Okay, let's say where the robot is. Robot should do something, right? And should go somewhere to do that. So where am I going can be called goal localization, where my goal is and where to go there. How should I go there? Robot asks himself or herself that how should I go there? And if we are going to answer this question, we say we need to do motion planning for my robot. And if you want to answer all of these for robots, your robot should receive the information from environment by sensors that it has, analyze them, then localize the robot itself there, and design and predict the next move of the robot. And if we compact all of these together, solve together, also we can call that you are also solving, for example, one SLAM problem. There are some important topics in mobile robotics as kind of most important robotics technology. Current state estimation, where is my state now? Finding position and state space. State space means that if you freeze the time now, this is very popular in machine learning and reinforcement learning and artificial intelligence. Wherever you are, if you freeze the time, that can be one state. Small change in the environment can be next state. Next change, next change. So we can discretize kind of environment to a small amount of time. Can be 1 second, 1 millisecond, or 1 minute. Depends on the level that we want to do. We call all possibilities in there as a state space. So like chess, if you have all possibilities, can be called state space. And our robot usually tries to understand by sensors what is the state. That this can be used by landmark, like by perception, seeing what are the objects around the robot and understanding where it is. And of course, we have concept of noise, error that you have there. That in algorithms we try to also later consider those noises and understand, okay, how we can fix this by advanced techniques like Kalman filter, extended Kalman filter, for example. Or simply if else is that is okay. Then localization, we discussed about it. The mapping, we discussed about it. The SLAM, we discussed about it. Navigation. Navigation means that, okay, how to control robot to move in the environment. I know my robot knows that from room A goes to room B. And I also have the path with path planning. But how to navigate, how your robot should say, okay, this is the path that I have, and my structure, if I'm walking, if I'm moving, how should navigate there. So this is called navigation in mobile robotics. We have motion planning that I discussed about it, and like all of these are kind of some examples that we are faced with in robotics, especially mobile robotics. If we want to talk about a general view of robot control and the evolution of the robot control, so for now we know what is the robot, and we know that robot can be two types, fixed or mobile. And we need to know, we know some algorithms and some general topics. But what about the control? When we are talking about control, we mean that how your program controls your robot to move. If you have arm, how your robot moves. The general evolution of robot control started from 70s mid, that we had classical control, no need for any sensor. You have motor, you write this motor, go to this position. The other motor go to this position. And with this routine, you can control the robot. If I give you a real robot and I say, go from A to B, you most likely start to do the same thing. Then in 80s we started to have reactive paradigm. That in this reactive paradigm we didn't have model of environment, robot didn't have model of environment, but heavily depending on the exact sensor reading. For example, okay, from A to B, robot wants to move, but also wants to read the sensor and says, okay, if the distance is smaller than X amount, then stop. So this is called reactive paradigm from 8th century. Then we had the hybrid robots that they had the model of environment in high level. It means that they had some understanding of environment, where should be for example, the obstacle in the model of environment. Then try to combine that with the sensor reading and the how robot moves. And later we had the probabilistic robotics after 90s. Then what does it mean? It means that we wanted to model the observation and we wanted to combine the model and observation together in a form of probability. That this is where advanced algorithms like Kalman filter plays role. How to have two steps of correction and prediction in order to bring probability into the game and correct those. So if you are interested in on this topic, in the control of these things, you can have a look at my other lectures. Anyway, exactly how we can formulate, for example, LiDAR scanning, probability form equations, and bring it into the very complex model of control system. And here we are aiming to reduce the amount of noise and understand the noise. So this is called probabilistic robotics. If you want to have a look at robot classification, we can say that we have indoor robots, including home robots, so class of home robots. Class of home robots can be a service robot, can be a sweeper robot, and any kind of robot that works in indoor environment as home robot. Sweeper robot means that a robot that you can buy in market and move in the they usually move autonomously in the for example room and clean it. So a second category of indoor robots, we can say we have entertainment robots. That entertainment robots are, as the name is on it, for entertaining you, kids, yourself, or act like your puppet or dog. As third category of indoor robot, we have teaching robots. For example, the Pepper robot that you can see here is one of the famous robots that try to teach skills to human. We have mine robots that they are usually used for exploring the environment in the dangerous and risky environments, and etc. as indoor robot category. On the other hand, we have outdoor robots category that we have unmanned aerial robots that they are usually flying for different applications like surveillance, rescue, air vehicles, or for example delivery package from destination A to B, like Amazon trying to use it. In outdoor environment, we have very interesting tasks of space robots, for example, rover that does space exploration. On the other hand, for outdoor robots, not only space robots, we can have underwater robots that they are working most especially as practical application for welding underwater, for example, for oil pipes or different constructions that we may need to do underwater, and it's very hard for human to breathe there, or we have limited time that we can send a human there, but robot can work for a long time over there without any problem. Monitoring and different many applications. Plus, we can have unmanned vehicles. That unmanned vehicles as robots can be self-driving car that you see a fancy example here, and as you know, can be a taxi that we can call them not only not only autonomous cars, but also they can be robots that doing something similar in the environment. So here we will have some more examples of robots. For example, as entertainment robots, you see in 1999, Sony launched first robot built for entertainment, and in 1999, all of 5,000 robots built were sold in less than 1 hour. And that was very interesting starting point to show that how people are interested in entertainment robots. We have home robots that can do service, teaching, vacuum, and help. And we have space robots that you can see Robonaut 5 here, that from NASA, and it is trying to help in space missions in order to explore environment and some tasks that is very risky for human to do. And as I remember, there was a competition 2 years ago around that Robonaut 5, and some researchers, any team could have been participating in this competition, and the winner would get the 2 million prize plus ability to run the. They intended to first simulate, because we have good simulations of this robot, work on simulation, and if it was working, the team were supposed to launch their example code in the real robot, and even if it's successful, send it to the mission and run it in the space. For home service robots, of course, robot that we can explain that how we have different kinds of robots that can help in household chores, or even elderly people helping taking care. You can see different examples of famous robots here, and you can see the Asimo that everybody knows. Pretty old design for that, but nowadays we have very decent achievements with recent new developments of robots for service. One of the industrialized, commercialized robots in home service applications, as you can see in many of the markets, is vacuum cleaners that you can buy any local market nowadays also. And some of them are claimed that they can even clean the space over 97%. They can find their own charging location basically and recharge themselves when they run out of the charger. And you can see different types of robots that here. The one that is in middle is like over 15 years ago that my team and me, I developed this robot, and it was at the time there were no commercialized too much. They were like very new, wanted to start the idea. And the interesting thing is that it was very successful project. Even after commercialized versions came, its performance was higher than many of those. One of the interesting robots that we can have is humanoid robot. Humanoid robots, for first time introduced in 1996. Honda as capable walking and carrying objects and climbing stairs robot that they are mostly designed for human design environment. It means that our environment, if you look, is specifically designed for human and is more adaptable, much better for humanoid robot. If a robot looks like human, can be used the objects, tools, and all the, for example, stairs and everything easier than other kinds of robot that we can have. During years, there have been many different developments for humanoid robots. When we call humanoid robot, usually we refer to a robot that can walk with 2 legs, or we call it as bipedal robot. You can see, for example, now open source humanoid robot here as one of the 2 famous and old platforms. We have the Asimo robot, or we have Boston Dynamics nowadays as one of the astonishing robots that can do very complicated tasks. There are different applications and different scenarios that we can use humanoid robots. One of the objectives also, one of the challenges for humanoid robot is that uh, in uh, in competitions like Robocop, they define some objective that if we can develop humanoid robots that after like before 2050, if they can play against teams like Real Madrid and Barcelona. And why playing soccer is important, why we should care about entertainment like soccer with robotics, it means that the reason is that if a robot can play soccer, if a robot can play like very difficult tasks like soccer, of course that robot is very capable to do anything else. If a robot can walk, jump, kick, and do all the complex and things that an athlete can do, then of course that robot is pretty capable. And this is the objective that is defined for robotics by some of the well-known competitions. For example, Robocop to play against big teams before 2050 and even beat them. For example, we have small-sized robots, Darwin, OP humanoid kid-sized robot. Again, we have now robot for playing soccer. We have some 3D printed pretty good robots like Nimro humanoid team. We have my own team's design robot that is like for 6-7 years ago with with some trophies in world-based competitions. We have Charlie humanoid robot and many different versions of robots that you most definitely have seen in social media. They usually categorize in 3 sizes or 2 sizes. They usually categorize in kid size that based on their height, teen size 80 to 140, and adult size 130 usually to 180. That categorize these robots in different kind of ages, but based on their heights, because age doesn't mean for robots that much strictly. So, other example in robotics, if you want to have more look, we say usually autonomous robots must have robust automatic navigation and positioning, otherwise they won't be proper device. If you want to always control your robot with joystick, of course that's not very capable. So this can be autonomous robot that I mentioned to you. We can have like applications like mapping, understanding of the environment in different layers in order to control robot autonomously, in order to robot understand the surrounding environment and act in the environment. And this can be a simple example that any starter student can do. Instead of like working on very fancy robot, usually we have two-wheeled simple robot and very man-made, handmade simple environment. Then based on that, your robot can try to construct the map of the environment, understanding of where are the obstacles, and based on that, where the robot is. Another example can be drone robot. So if I can play the video, so we can have flying robots. Okay, sadly I couldn't play the video, but later try this link and have a look that you have a robot, flying robot that flies and goes into the building, and at the same time here in the left side you can see that robot is trying to construct the map. After some moving in the environment, it can understand where the robot is and what is the map of the environment. So this is another example of the robots in the environment, and different kinds of robots that you can work on as flying type of robot. That they usually have the type of brushless DC motors that the DC motors are very fast, as like for example quadrators, and then they can fly in different directions. They have usually self-balancing sensor called IMU, inertial measurement unit, that you can understand the root PGR or angle of the robot, how much is balanced or not, and based on that, the same circuit design, same programming that you have, you control your robot in order to self-balance and even move in the environment. There are, of course, plenty more examples. Here you can see an interesting assembler robot that robots try to construct or even make complex tasks in manual mode. That you can see the robot is here designed to create a path to move, or designed to construct something by having some brackets. So this can be simple control by understanding and sensing, or this can be autonomous. And even you can imagine if you have multiple of these robots, how this robot can act in the environment to construct something, the things that you want. As I told you, we have the concept of probabilistic robotics. So because today I'm going to shortly talk about different general introduction, of course I cannot go into details, but I want to give you the general intuition of the different important concepts in robotics. We say we have probability theory that is aiming to cover uncertainties, and in the simplest form to understand probabilistic robotics, I can explain to you this. Like, you have a robot in the environment, in XY, in 2D, for example, somewhere in the room, right? So this is real robot position. Now, if we want to estimate model of uncertainty and bring it into the probabilistic robotics, it means that robot knows where it is, maybe using sensors, but of course it's not accurate and it has error. And usually we show it in probabilistic form, and it can be a distribution like this. And how much this center, so this distribution shows how much robot is sure that where it is, how certain knows that where it is. If the peak is too high, then more likely robot is in the center. If it's less, then the certainty is less, the probability of the distribution is less. And of course, in other lectures that I have, I'm going exactly in details of how we can bring it into the math, how we can use probability form of the robot location, and how we can bring it in this probability form, and based on even the camera and different sensors, and generally how they work. And if you are interested in, just look at the courses. Either you can look at the YouTube courses that I have, or you can study in probabilistic robotics book. So the robot movement can be mapped by distribution estimation. Usually there we have how we show the distribution. We say probability of the x, that is robot pose. It means that x, y, and theta, that is orientation of the robot, the heading orientation of the robot, and map. So these x's, the series of x's 0 to t, and map usually is given by what? Given by observation 1 to t and control command 1 to t. So it means that robot observes, and there are some control commands that come in: move 1 meter, rotate, move 1 meter, rotate. So these two as input in probabilistic form will indicate our map and robot pose. So this is called probability distribution of probability presentation of robot. If you want to do like path planning or localization, then we can say, based on what we want as output, we can have different techniques to do this approach. There are different robotic solution approaches, as I mentioned, but there are also different classes for them. For example, we can have real-time robotics control that in limited time robot needs to react in the environment. These are called real-time. Robot real-timely need to act. For example, flying robot is a very nice example. And that being real-time is depending on amount of processor power of processor that your robot has, memory, and many different effects. On the other hand, we have non-real-time robots. For example, this assembler robot, maybe we don't care, even it takes 1 hour to bring one bracket here. Of course, we do care, but I mean, some applications are not necessary to be real-time. If it takes 1 minute or 1 minute 10 seconds, we don't care. But in flying robot, if you delay 1 millisecond, your robot falls. If your humanoid robot is trying to walk, the trajectory of walking is like 1 second late, then fall, like human walking. So which one is better? If you want to ask, we can say the one that is depends on the applications that we have. Another category, we say we have passive robots control. In passive robot control, robot usually does not make deliberately decision about what is going to do, only sensing the environment and for example, mapping. For example, if we have one talking about an example of passive control. On the active control, robot tries to, by purpose, in order to solve the problem, also have the control based on the controller. This is called active control. That means that, okay, if I want to, so it means that like, meanwhile that robot is moving in the environment, just understanding them of the map and localization, for example, but an active control by purpose goes to see where it is and what is this room, what is that room. That can be called active control. Another category can be called single agent robots, that you have one robot only, or multi-agent robot, that couple of different types of robots working together. Which one is better, of course, depends on what we are going to do. Also, it's open problem, and still researchers are working on that. Other complex problems can be planning, design, task allocation, dealing with defects, dealing with variability, dealing with inventory, and etc. Different complex problems that we can have in robotics, and each one of these have like hundreds of different studies, and I can say for each one of them hundreds of different complex algorithms that if you are interested in each one of them, you can have a study. So as one of the interesting tasks that today we a couple of times mentioned is localization. So localization means that if you have a robot that moves in the environment, says where it is, so you can see that based on some landmarks, seeing like this tree, that water, that tree, this tree, based on the distances that I'm finding where I am. If this happens by observation, like camera, this is called visual. If no, instead of seeing, we say, okay, if you are closing your eyes and walking, you can understand, okay, I rotated 90 and I walked 10 steps. So if you do this, either in humanoid robot or wheeled robot, we call it as odometry. In visual, usually we have robot sees the environment based on visual features, understand moves based on the time sequence, and then estimates where the new location is. So these landmarks can be also building, can be features of the environment like edges, corners, or other features, and it's very common to be used also in autonomous wheel cars. You can see the LiDAR scan of the car here. Could be a robot that scans the environment. In visual localization, we usually can talk in robotics. We can talk about sensor fusion, that if your robot sees, and if your robot has a scanner, and if your robot measures the distance, combination of all of these, how should be. And in odometry, we say estimation of how much robot is translated and rotated in the environment. And there are many problems here. For example, uncertainty, slippage of the robot feet, the motion execution accuracy, the sensor accuracy, and etc. challenge that we have over here. For example, the robot is rotating and moving from A to B, but amount of rotation and amount of movement both has error, and this causes accumulated error at the end. Apart from all of these, that we have different approaches. We understood the general robot and we talked about the different perspectives, different applications, and different techniques. One of the recent trends that I want to do a little bit emphasize nowadays is that if you have robot structure and your observation sensors, is there any way that don't say anything specifically to robot what to do? Like human when born learns how to do and interact in the environment. Can we have algorithm like this? The answer is yes. With recent advanced achievements that we had, now we can have some algorithms that let the robot learn itself. Learn with the mechanic and sensors and everything that it has itself without we saying exactly the sequences of action and everything specifically. This is very interesting that we can do, and this series of algorithms is like third class of algorithms. We have supervised in machine learning, we have supervised and unsupervised reinforcement learning. That in reinforcement learning, the robot can interact in the environment and learn itself. And you can see one of the most advanced simulation here called Isaac Jim, that there are different kinds of robots you can see, and each one of these robots, including fixed and mobile robot, that they learn by interacting in the environment. Like if I have the cup here, if it's hot, if I touch as human first time, I will understand that if I touch something hot, my hand burns. Or if I drink it, if it's sweet, I like it, so I get reward. So based on the reward and punishment, by interacting in the environment, robot can learn. And we have pretty decent advanced techniques that we can use for robot learning, and nowadays became very popular in last 2-3 years. Of course, we are not limited to robotics with reinforcement learning. It can be applicable in like chess game Go, and many different games. Again, for this one, I have in detail lecture. If you are interested in, you can have a look at my lecture at YouTube later. Unfortunately, I don't know why I cannot play the video. Here we have, I had the project that robot learns with deep reinforcement learning how to interact in the environment by carrying heavy objects. For example, you see, if I couldn't play the video unfortunately, but if I play the video, the robot walks backward and learn how to carry even heavy objects, even me. So this was first time that is happening in this applications, and you can have a look at the publication in detail. This work has been published, and robot in the simulation learns how to drag different objects, how to control itself, and here is able to even drag object like me. I think the video also, I have the video on YouTube too. And here you can see the general architecture of how robot is working. And if I want to conclude today, we understood what is the robot. We understood what is the fixed and mobile robots together, and what are their differences. We discussed what is the common types of sensors. We said we have visual, tactile, for example, and different kinds of sensor. We saw a general robot design architecture in different layers, and I said that all the robots that we have are basically following that rule in simplest form to very complex form of the robots. We saw application examples of robots in different areas that most likely you have seen many of those in social media, internet already. So as practice also, don't forget to go to slide 28 and find and classify assembler robots that we can have in terms of their design and applications tasks for today's lecture, and classify them to see what kind of robots that we can have. For example, due to limitations of today's lecture, if you have soft robotics that they are working based on muscle and they don't have joints and the actuators, how they are working, and or or for assembler robots, what kind of applications they are and what they are doing in groups together. So you can create a tree in order to demonstrate the classes and the applications, and even you can have a look at the publications and sort them for this course as practice. Thank you so much. If you have any question, feel free to contact me through the email that I proposed to you, and hope you enjoyed today's course. Thank you so much. See you soon.